a nice background with the American flag and stuff. If you want it, I can do it in there, but it's just there's people walking around, and if I start talking about matryoshka brains, it's going to be like a bit weird.
No, all good, man. All good. Do it here, and then you can just, yeah, if you got any cool photos like that, we can just overlay them before we
Sounds good.
publish. All right. So that should be recording. You got a notification?
Yep.
Yeah. Awesome. All right, Philip. Thanks so much for joining us at Dyson Sphere Time. Great to have
Thanks so
you.
much for having me. Thanks so much for having me.
You are, I think it's fair to say, leading the way when it comes to actually making compute extraplanetary. How does that feel?
Uh, I mean, so, some days yes, some days I question if what we're doing is complete insanity, and some days it's very exciting.
Well, I think it looks like a lot of people have been inspired by what you're doing because, as we saw in our last episode, there is a lot of activity in this space. The rest of it seems to be mostly talk and some big chunks of money, but you're actually putting, rubber to the road now. And you said you've got a launch coming up, just delayed slightly to November.
Yes, yeah. So we'll be launching a demonstrator satellite. It's a size of a small fridge, like a 60 kilogram small sat, about 1 kilowatt. So we'll be the first to have H100s from Nvidia on that, an A6000. So it will be about 100 times more powerful GPU compute than has been in space before. And yeah, the purpose of that is just to prove that our radiation shielding and thermal management techniques allow us to operate high-powered compute or high-powered GPUs in space.
Yeah,
Um,
very cool. I want to dig into some of that because I know that the thermal stuff in particular is where you're, really cutting new ground there.
yeah, for sure. So we're a team of about 10 now, or nine engineers and me. Four of those engineers are working on making these chips work in a high radiation environment. So that's shielding and then software to, voting algorithms and things like this. And then five of the engineers are working on building a very large, low cost and low mass deployable radiator. So that's essentially the core IP that we're developing. And then we've outsourced the bus. And yeah, the core challenge of a Dyson Sphere slash Matryoshka brain is the thermal and cooling part. And I know you have some interesting ideas about flying much closer to the sun, which we should definitely talk about.
Yeah, yeah, that'll be fun. That'll be fun. Before we go there, tell me about the team because I've seen a few announcements about your team. You seem to have the all stars together. So who's working on this?
We have the absolute all-stars. Like, yeah, if we're gonna do this, we need basically the best space engineers and the best like hardware GPU guys in the world working on this, and we actually, I think we have that. So, for example, we've got the guy from NASA's JPL, Jet Propulsion Laboratory, who designed the radiators for the Europa Clipper mission. He also designed the radiators for a recent lunar lander, the successful one. I can't say which one, but it's the one that landed.
The one,
Well,
yeah.
the one that didn't fall over. Um, and also for three of the NASA payloads on that. So he is one of the world's experts in thermal design. We also just recently have made an offer and signed with somebody from Kuiper who's been a senior thermal engineer there. So on the thermal side of things, and then on the structure, like the mechanical design of the radiator, we've got a guy who spent 4 years at SpaceX, and then was 3 years at Helion Energy designing the arc fusion crucible, which is all about heat dissipation, basically, at Helion Energy. And then before that, he studied mechanical engineering at MIT. He's leading the actual design of the radiator. So I mean, yeah, they're a phenomenal team.
So does that make you the Zuckerberg of space-based data centers, given how many like amazing people you've captured?
Uh, if I say that, they're going to start asking for $100 million. So I
Got
better.
it. Got it. These people look, you took them in. I got it. All right. Cool.
Like, it
Okay.
wouldn't surprise me if, I mean, yeah, I mean, we're certainly paying, we're paying market. It's not like we're paying below market or anything. Um, yeah, it wouldn't surprise me if we start seeing that, be a tighter talent for this type of, a tighter war for this type of hardware talent than there's been in the past.
Yeah, well, I guess it makes sense for anyone who's interested to get in early with you. So there's some equity there, and things can be really interesting given how at the front of this you are.
Yeah. 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 It looks like I think we'll probably not hire again until the Series A. But yeah, we'll be 11 people basically. Yeah, we could easily triple the size of the team now, but I want the team to be as elite and talent dense as possible. So we're keeping it deliberately small.
Yeah, awesome. Love it. Okay, so this is Dyson Sphere time because I'm obsessed with, turning the galaxy into computronium, or probably more so than that is just getting industry off the planet.
Yeah.
And I
Actually,
think,
can I interrupt you there?
yeah,
Is it just the galaxy? Have you ever thought about why we're not talking about Kardashev Type 4 civilizations? Like it really pisses me off that it finishes at Type 3. Well, like why? It's so arbitrary to finish at Type 3 when
I
the
think that's
clear
a fair
Type 4
point.
out there.
Like it's anytime you look at a piece of matter and it's not doing some kind of calculation, you're just like, what's wrong with you? And that could be anywhere. Um,
But it wouldn't,
yeah,
I mean, it would only take a billion years to get to the nearest, to get to Andromeda if you were going up. I think you need about 700 kilometers a second of delta V to get to Andromeda in a billion years. And billion years, I mean, yeah, the galaxy and the universe is about 14 billion years old, but we've got a long way to go before the expansion stops anything expanding. So why stop at Type 3 civilization? Why not go to Type 4 and make all galaxies, um, absorb the energy of all galaxies?
I would like to see the TAM slide on that, Philip. Yeah.
Well, there's a trillion galaxies, and each one has 5 trillion planets.
There we go. Total addressable matter. I think that's
Yeah, yeah. There is that number does exist, and we should figure out.
yeah, that would be good. Yeah, we can do the maths on that. Cool. Okay, so um, I think what we can, like do quite practically with what you're working on is really get industry off the planet completely. And I think data centers are the most sensible thing to do first because you're only needing to transfer bits and not atoms. But later on, we can move all manufacturing to space and keep
Oh.
Earth for people, plants, and animals, which I think it's a pretty good home for. I think humans aren't a great form factor for being in space, at least not yet. Maybe with some upgrades. Um, but data centers make a lot of sense there. And so, just how much can we do there? And that's what we want to explore on the podcast that we're doing. So
Hmm.
you've got this demonstrator that's going into Leo, and we've spoken a bit about that previously, where you've got this dawn dusk orbit, so that really reduces your launch costs while still giving you the 24/7 solar. Um,
Hmm.
but have you thought about what it would take if we sort of crossed that threshold a bit and went closer to the sun, where, yeah, there's going to be a bit more launch costs, but you just need to bring far less panel with you?
I was thinking about it when the main time I've been thinking about it is when I see your posts about it, to be
I'm
honest.
glad to be an inspiration.
I haven't been down a Grok 4 rabbit hole with this yet. Because
Yeah.
anytime I want to test any of this stuff, I go on Grok 4 heavy and I'm like, how much is the launch less mass do we need? And like, what is the temperature if you're half the distance to the sun and all that stuff? I haven't done that yet. How close are you envisaging us being to the sun? Because I know it scales with the square of the distance. So if we're half the distance is a quarter the size of the panel we need. But go
So
on.
the number that I've sort of come to, and you're free to dispute this, is about 0.04 AU. And the reason of that number is that's where Parker Solar Probe is going. So it's
Well, it
already
also
gone
does
there.
flyby. Yeah, it does a
Yeah.
flyby.
So it's doing a flyby at that distance, which means that humans have successfully made something that can survive at that distance from the sun for, a significant amount of time. So we do have the capability to create something that can thermally survive there. It might be a little close because there's a bunch of stuff sort of splashing out from the sun that might damage it if you had, but if you had a lot of stuff there, like it'd probably work out. At that distance, you're going to get about 800 times the radiance per square meter that you would get in
Yeah.
Leo.
Yeah.
So you need 800 times less panels. It's about I think it's about
What's the
1200.
delta?
Sorry?
What's the delta V to get to a sustained orbit but not elliptical? What's the delta V you need to from Earth to get to that, you know?
I did run that a little while ago. I think it was like you needed like 30,000 to get there and 30,000 to slow down, something like that.
Kilometers an hour. What's that in kilometers a second?
I'd have to
Okay,
do a rapid grok rabbit
yeah.
hole to figure that one out. But so okay, so hear me out. So I did go pretty deep down this rabbit hole. So the problem was you basically just needed like absolutely massive rockets, and that's why the Parker Solar Probe was needing to do like sort of 7 slingshot maneuvers to get
Yeah.
there. Originally, they thought about using Jupiter, and then I think they ended up using Venus because it was just going to take too long with Jupiter. Although it took quite a amount of time with Venus as well. And that's where I got into the idea of like what we really need is some basically some rail guns, some mass drivers. And so like yeah, so the first catcher that you need to send up there, you'll need some chemical rockets to put there, and it'll probably be quite an inefficient number of chemical rockets to put it there. But then when
Mm.
you've got a rail gun sitting, in like sort of, near
Leo.
Sun orbit, and then another one in Leo, and you can just shoot the stuff, and as long as your aim's good enough, you can just catch it at the other end.
Why do you need to catch it at the other end? Why don't you just shoot it at a velocity such that it slows down enough at the other end?
I haven't modeled that, but I feel like it's just going to like ricochet off. I mean, you'd have to get in a very tight
Yeah,
solar
yeah,
orbit,
you'd
right?
need it
Because you
would
won't get
require
any atmospheric braking around the sun, or if you do, it'll be like, billions of
yeah.
Kelvin of plasma or something, which is probably not what you want to interact with.
But all right, so let's assume that that's possible and we can get a bunch of mass there quite cheaply. What size radiator? And I guess the radiator is like sticking very long out the back. So you have this face and then you have an extremely long
Yes.
radiator out the back, which kind of actually makes orbital, it's kind of a stable architecture because actually if you have a very long thing, that's the way it's going to orientate itself anyway because of the gravity gradient between the front and the back.
Yeah, right. I didn't think of
Um,
that. That's cool. So save a little bit on station keeping.
but how long does that thing have to be out the back? I mean, it has to be like very long, probably like thousands of kilometers to dissipate that amount of heat. And then how are you pushing the heat out the back there? Like,
Well, I mean, that's what
oh,
I came to you for, Philip. You're the experts on the heat dissipation. But so what I thought, right? So if you've got a 4 by 4 kilometer solar array with a 1 by 4 kilometer radiator on it,
yeah,
so
yeah,
we go and turn that. So now it's a 1 by 4 kilometer radiator, but it's a meter wide or whatever you need to
yeah,
sort of run those tubes. Then we only need enough solar panel on the face such that the light from the diameter of the sun never catches the back of the radiator.
yeah. Let's go with that. Yeah, let's presume that's correct.
Yeah.
Probably. I mean, that makes sense. Yeah, that's how the Park probe does it. Yeah.
Yeah. Now you'll have a bit of length there, which means you'd need some more pumps or whatever you're needing to move that fluid, and there might be a bit of inefficiency over that distance relative to having the radiators sort of mounted more flush with the compute or the panels. There'd be like maybe a little bit more distance there. Um, but that was the concept because if you make the panel 800 times smaller, then you're capturing the same amount of heat that you would near
Yeah.
Earth
Yeah.
anyway. So that you'd need the same radiator, I assume. Like there's not going to be much sort of passive heat in the space just near the sun.
Hmm. I don't know. It sounds like an awful lot of effort to go for to have a smaller solar panel, given that the solar panel is dirt cheap anyway.
Yeah, okay.
Solar panel is not the expensive part of all of this.
All right. So on a pure sort of cost efficiency basis, you would say, look, do what we're doing now, but just spread it out at like a 1 AU radius and just have a shell of the exact configuration you have today.
Yeah, yeah. Have you ever come across this concept of a chain of, so like the further away from the sun you are, the slower your orbit essentially relative to the ones that are closer. But like the faster your absolute speed, the slower your orbit. Um, there's this concept where if you want to have, let's say you want a chain of objects that orbit at roughly the same speed around the sun, there's this concept where you have varying degrees of um, panel such that the outward force from the sun on the panel is enough to you're going slower, and so slower should mean you're coming in, but actually the force from the sun is enough to keep you where you are. And so it's basically like you have you could basically have like a chain of stuff to the sun, and what that means is you don't have this like data transfer latency problem. Have you ever come across that concept?
I haven't seen it. So you're basically using the panels as a solar sail to then allow them
Yeah,
to keep a constant distance from the sun, but at a lower orbital
yeah,
velocity than you would expect.
yes,
And so they're
and
sort
that
of forming this
enables
kind
you to
of
have this
tentacle.
chain. Yeah,
Yeah.
yeah, exactly. That's one concept I've heard um, discussed
Right.
where
And so that way, instead of having all these things that are constantly changing their distance relative to each other, you can just build sort of a straight highway if you had, a large enough solar panel to make a large enough solar sail to so you could slow
yeah,
down enough and buffer that. Wow,
yeah,
that's interesting.
yeah, yeah.
Yeah. Build a
Did I ever
highway.
tell you, you were the first person that ever told me about matryoshka brains, by the way. I don't know if you know that.
Really?
Yeah, yeah. And then you told me this theory that I absolutely love, but then you told me it wasn't true, and I'm like devastated. The theory that like 80% of the stars in our galaxy could already be matryoshka brains because of dark matter. And then I asked Rock, and it said no, because the points of light aren't pointy enough, or the
Mm.
points of dark matter are not pointy enough because you would expect it is
Oh, right. So they're not like
easily.
localized enough. They're not like, yeah,
Yeah,
okay.
yeah.
Yeah.
But I think this yeah, it could be something to that. Maybe the I'd like to because dark matter is such a bad explanation. Um, like it's as good as saying I don't know. Like as far as I can
Well,
see.
maybe the best place to build a matryoshka brain is around a white dwarf or something. So maybe it makes sense that they're not that pointy because it's just they
Yeah,
only
yeah,
do it for the small, older ones or something.
yeah. I mean, I think even white dwarfs are too pointy
They're
versus
still
what
too
we
pointy.
see. But yeah, but maybe there's some. I don't know. Maybe there's
Maybe you
yeah,
can chip a bit off and like, have your own little fusion reactor. You go and like harvest a bit of
yeah, yeah.
star.
Yeah, I mean, it could be. All right. What's your explanation for the Fermi paradox?
I don't know. I think I always just look back to the XKCD on this one where it's like there's this big equation and like one of the variables is just the amount of like,
Probability of life spawning
well,
or
the amount of like, BS that you're willing to buy from Enrico Fermi. It's like, like who actually gets to set that constant, right? It's like what's the reason that life should have any particular probability of occurring? And
well, maybe true, but I think if the probability is anything under, there's 5 trillion planets in our galaxy and it's been going 10 billion years. I think if the probability is anything more likely than 1 in 5 trillion for 10 billion years, then the galaxy should be populated pretty quickly and we should see life everywhere. So I think you have to then assume that life is very unlikely, which I think is just like a dangerous place to start an argument, or like a
well,
seem
okay. So
plausible place to start an
right.
argument.
So let's say that, life is actually like, reasonably possible and reasonably likely, but someone's got to be first. There's got to be the first life somewhere. And maybe we just had the conditions go right for us, far earlier than most.
Well, that would mean life is pretty rare then. Like if we're the first, that would mean there's been 10 billion years with 5 trillion planets, and we are the only ones that have created intelligence or superintelligence.
Or maybe like there's the billion others out there, but they're still monkeys.
Also possible, but all I'm saying is to get from our level of intelligence right now to colonizing the galaxy is definitely less than a few million years.
Yeah.
So I don't know why. All I'm saying is there's nothing out there that is our level of intelligence yet, or there is, and in my mind, the much more likely explanation is that for some reason intelligence is pretty short-lived. Um,
Yeah, I mean that's sort of the more bleak view, I guess. I don't know. I think like we're reasonably resilient. Like we seem to have made a lot of different ways to really cause problems for humans and somehow like, muddled our way through it.
I don't know. To me, superintelligence is quite different. Like, the fact that there's nothing else in our galaxy and our galaxy looks so dead, to me is very worrying. I buy the argument that the most likely explanation is that intelligent life is very short-lived.
Very short-lived. Man, this is getting bleak. I wanted to talk about
Yeah, yeah.
satellites everywhere.
That's why I'm so passionate about like interstellar exploration. I want to prove that colonizing the galaxy is actually pretty easy to do. And if you can prove that, maybe people will start taking it seriously, the Fermi paradox. And maybe then people will start to be like, shit, maybe we should actually, like, in the next 50 years, consider why there's no other life in the galaxy. Like,
Hmm.
be drawing attention to that fact, I think would be a valuable thing to do.
Or maybe we could just try to colonize the galaxy. Like
Well, I am
everything's,
trying.
eh, I mean,
Yeah, all right.
everything's feels so expensive because we've just got all these like, like a lot of preconditions these days that, there has to be certain levels of safety applied to everything. And you go back like not too long ago and people were like, yeah, just sort of grab like enough wood that it floats and throw people on it. And if, only 80% of them make it, well, then that's who made it. And I think if you sort of apply that to spaceships, they'll probably cost, a hundredth or a thousandth or something.
Yeah,
Um,
I'm fully up for trying to colonize the galaxy as soon as possible.
cool. Okay. All right. Well, yeah, I don't look the doom. I don't know. I can't. I think it's all too amazing. Maybe that's my problem. I'm just like, this is so exciting. How could it go to? It's like,
It
I don't know. Is
is,
it going to be
I agree that
Terminator?
it's amazing. I'm not saying it's not amazing. I just think there's probably thousands, maybe hundreds of thousands of civilizations that have thought this is amazing. And within maybe 100 or 200 years of getting super intelligence, it stopped to be amazing.
Hmm. Okay.
Yeah.
Okay. Look, I'll meditate on that. Okay. So. We want to get out there because look, in case you're right, we at least want to spread out a bit so that there's I did do this little bit of a chart where said, look, this is I was looking at all this life extension technology and how we can sort of replace organs with robotics and make sure like really like no one should be dying of a heart condition because we have robotic hearts that work fine and they should just be made on an
Yeah.
assembly line and that kind of thing. And I realized after looking at this that this is the closest humanity might ever be in terms of like time and space between people. So you go back not too long ago and you could measure that all these charts, you could measure, how far apart people were in terms of, days to reach each other or months or years to reach each other. And then also for communication, like how long it takes to talk to each other. And we've done such a good job with travel and fiber optics and satellites and everything else that we're
Mm.
actually extraordinarily close to each other right now relative to any other point in history. But as soon as we get this ability to move in an interstellar way, we'll be much more spread out. So this is sort of a really
Mm.
key moment for kind of defining, what humanity is, because we had all these different experiments of what humanity is, and they all come together and kind of, got a lot more in common with each other. But they're about to go out, and if you've got people heading off to different star systems with, forget physically reaching, but not even having communication reach each other for years or 10 or thousands of years. Like we're going to have a lot of different versions of humanity that are, quite disparate.
I hope so.
So maybe
Yeah.
maybe some of them will have the bad super intelligence, but maybe some of them will have the good super intelligence, and
Well,
there'll be a
all I'm
bit of a
saying is
space buffer.
if there had been one in the history of our galaxy on any planet, then the galaxy would have life everywhere. That's all I'm saying is it's like seems pretty unlikely that we're the first to me, but maybe we are.
Do you
Do you know?
think like how much of that sort of thing do you think is based on the idea that, the speed of light is something we can't, really meaningfully get past?
It's totally fine. I mean, what I'm talking about is that do you know what these von Neumann probes are? They're
Yeah.
basically, yeah, you send like a probe that can replicate and then go to another star and go to another star. Like that is like an incredibly simple piece of technology. Like that is not like that's like in today's technology, an incredibly simple piece of technology. So it takes 57,000 years at the slowest delta V to get to Alpha Centauri with one of those probes. It gets there, it replicates itself, it goes to the next star, it goes to the next star. If you do that, even just because of the mixing of the stars, you yeah, you pretty much colonize, or you pretty much get to the entire galaxy within a few million years.
Yeah, right. So we should have seen a probe by now.
Really, there should be probes everywhere. It shouldn't be difficult to see probes.
Mm.
And it's not the smart ones, like the probe, the von Neumann probe is what you send now with today's technology. Then, in 100 years from now, we're going to send cool stuff that will actually build cool shit everywhere. And like, no.
Yeah, I don't know. Maybe religion's the answer, Philip. Maybe that's why. Maybe we're just really special.
Either religion or the what do you call it? The simulation hypothesis.
Yeah.
I sort of kind of buy into that at the
So
moment.
religion, simulation, or superintelligence is short-lived.
Of those, superintelligent is short-lived is definitely the most likely one.
Okay, well, let's accelerate that as much as possible then. Um, so, uh, so your tech, so you've got the radiation and the cooling that you're working on. How much? So you did a radiation test recently, I think.
Yeah, we took some H100s to the cyclotron in Knoxville. And I think we might be the only people on planet Earth who know at what radiation level H100 will fail at.
Yeah, right. Okay.
And I don't intend to reveal it here today.
Sure. No, that's okay. All right. But you've got some good data there on just how much shielding and of what type that you're going to need to protect these things.
Yes.
Um, and I sort of look, I said it's, 6,000 or 8,000 Starlinks. There's, people in space on the ISS. To me, it feels like, maybe not in a cost-effective manner, or maybe with Starlink, but like radiation is like, feels like it's sort of, I don't know, there's some prior art there you can work with.
Yeah, it's definitely solvable. And it becomes a lot more solvable with Starship and with less mass constraint. You just need to, yeah, you can solve it either through hardware or software, and ideally a combination of both. And basically, the bigger a satellite gets, the lower a problem it becomes because the compute on a satellite is the volume of that satellite, whereas the shielding is the surface area. And so the larger the satellite gets, the lower the proportional mass that goes into shielding.
How much does the compute kind of like take one for the team? If you keep putting more and more compute around the compute, then is it then the shielding?
Yeah, exactly. That acts as shielding too. Yeah.
Yeah.
Also, you can put the radiator on the outside and that acts as shielding, and you can put batteries, things that are less sensitive, and that acts as shielding. Yeah.
Yeah, okay. And then the thermal stuff. So that's where like you're really putting things that are a lot hotter than have been, in a concentrated way and that have been there before. So obviously this has been solved for people and other satellites, but they haven't been trying to jam, Jensen's like, nuclear
Yeah.
radiators into space. So I'm assuming this is where, you're going to have to do more work than, than other people have had to do by a more significant margin.
Yeah, we'll have by far the largest commercial radiator in space on the second satellite launching in October next year. That's about a 10 kilowatt satellite. So that one, yeah, the big difference between what we're doing and other satellites is actually there are some satellites that have hot parts, but they just are not as densely packed as ours is. It's all about, yeah, the heat density on ours is way higher than any other satellite that's ever been in space. And that requires just a fast flow rate, higher pressure, um, active cooling system than anything else in space.
And something that's actually going to be, cost effective as well, which I
Oh
think
yeah,
is,
exactly.
yeah,
Yeah, we're trying to make these things extremely low cost and low mass. Yeah, I mean, the manufacturing techniques we're using are like trying to do it as dirt cheap as possible. I mean, it's not super cheap, the equipment, but it's a cheap, marginal cost once we get it up and running.
yeah, okay. So presumably, like, we've done many different things on Earth to deal with heat, and one of the constraints that we've got is we don't have a, 3 Kelvin or whatever the sort of the like black body kind of temperature is in space to work with. So you know, put a lot of runs on the board. Maybe it could be likened to the difference between, silicon and optical, processing where, optical might be a better thing. It's just that we've already invested trillions of dollars in making silicon down to X nanometers. And so you've just got so much momentum around that. And, like you
Mm,
can go and buy a, heat pump for your house, or, you've got all this technology that just assumes there's some medium to disperse the heat into that's been refined over years. And then when it comes to space, everyone's like, well, it's so expensive, so why would we bother saving money on the radiator? Because everything's already like we'll save money somewhere else because
yeah,
we'll make things cooler, we'll make things more efficient. You're like, no, that we don't have that option because we're putting Nvidia hardware up there. It has a temperature, and so
yeah,
we're just going to have to really figure this heat piece out.
exactly. That's literally it. Let me ask you, have you come across this idea of the total number of data centers we could run terrestrially being some number between about 10x what we currently have and 100x what we currently have, purely because of, so let's assume that fusion works, and let's assume that we don't have any, carbon emissions from fossil fuels or anything like that. But there is a amount of heat being pushed out into the atmosphere with each GPU. And there is some limit where you start boiling the oceans or you start having temperature rises that are like 15 degrees just because of the waste heat from these data centers. This is a topic that I see being talked about. Sam Altman's mentioned it twice in the last month. Um, we spoke with a guy called Jan Lek, who was a researcher at OpenAI and is now at Anthropic. He put in a very small angel check into the seed. And the reason he put the angel check in is he was like, look, I don't know exactly where it is, but I do know that the day is coming where we will not be able to build any more data centers on Earth purely because of this heat that is being pushed out. And so if you guys are getting started on this and it's, maybe it's in 50 years' time, that technology will be valuable and people will realize it's going to be valuable, on a much shorter time frame. In 10 years' time, people are going to be like, oh, fuck, we're like actually starting to warm the planet up because of these data centers. Have you come across that line of thinking? Or?
I did see Sam mention something about that, reasonably recently. Um, I think I think that's certainly possible. For a while I was thinking that before, I hadn't sort of done the math on Starship the way you had, and I was thinking, look, the solution to this is to basically get piles of solar panels, and we can't build the batteries fast enough, so just build big copper, you know, like ultra high voltage DC, like just wrapping around the world, basically. And so, because the sun's always shining somewhere, and I think you lose like 60% of your power going across the Pacific Ocean, which would be like your worst loss, and anywhere else would be a bit better than that.
Yeah,
Main
I see.
problems
Yeah.
would be just getting that much copper and the geopolitical risk. But there's of course, if you like, even if you take it in as solar, then you're not then the best place to put that's going to be a desert where normally you'd be reflecting that heat back out
Yeah,
into
exactly.
space. So you will
That's the
instead be
main thing.
retaining that.
Yeah.
Um, so I don't know. I mean, maybe you could come up with some, data centers that have got that kind of that sort of black body radiators on there, like in the evening, like trying to, when the clouds are away,
But
trying to emit some of that heat. But look, I think your approach is a lot better, and just from a cost perspective, it's going to make sense to do that before we. Well, I don't know, maybe not. We are building the data centers very, very quickly, aren't we? So.
mm.
Yeah,
I
somewhere
think
between having to do it
okay.
because of that and it being economically more sensible because of Starship and what you're building. Yeah, maybe those lines will be similar.
Yeah. I think I think it will be economical before it's a problem on the heating. I think the reason to do it will not be that we're worried about heating up the planet. I think the reason in like a 10-year time frame, the reason to do it will be the economics of it.
Yeah, so economics. So Starship, what's your, if you had to, speak on Starship's timelines, like what are your thoughts? When are we going to see the returns start to happen and then that unlock the value for you?
My guess is first Starlink payloads delivered to orbit end of next year. First commercial launches, which customers can book on mid 2028, so probably 2 years after that. And then volume Starship launches maybe 2 years after that. So early 2030s for volume Starship launches.
And that's when the full and rapid reusability is going to make it happen.
Yeah, yeah, yeah.
Okay. So if I can jump back to my idea about these railguns, because I got a little bit obsessed about these railguns.
Yeah, yeah.
So
So so the railguns are in Leo, and they presumably have a lot of mass themselves to stop them shooting backwards.
yeah,
Uh,
so they'd be quite heavy, but then they'd do their own station keeping with ion thrusters powered by probably some regolith or something like that. I don't know if you've seen the
yeah,
Neumann space drive where you can basically just you don't need like exotic gases or anything. You can just put stuff in them
silicon, whatever. Yeah,
and just shoot it
totally.
out at near sea and station keep. Not super
Yeah.
time efficiently, but enough to sort of solve that problem. Because my concern with Starship was like, look, I mean, obviously these folks know how to get a rocket up and land it, but what they're struggling with seems to be the thermals on this re-entry, and they've gone through these like many different ideas of like, are we going to, bleed some fuel out as like this sort of buffer? Are we going to put tiles on? We're going to put plating and tiles, but then we're also going to have the fuel behind it. I'm like, this is not
Mhm.
heading in the simplest solution. The best part is no part direction. We're just sort of adding more and more countermeasures to this heat issue. I'm like, why don't we just solve the heat issue? Because it's happening with the square of velocity, right? So what if we just drop um, what if we drop the speed of this thing by half? So it's no longer, in orbit, right? It's just going to fall and it's going to fall at a low speed. So how would you drop the speed of a Starship by half? Well, you fling it through a series of electromagnetic rings that will slow it down a lot.
Oh,
Um,
interesting.
and then you will not need you won't need you won't need tiles, you won't need plating, you won't need anything. You'll just need these rings, and then they'll just station keep with some dust, and
Don't the
then
rings get pushed out into wider orbits, and then I guess then you bring the rings back into a lower
bring
orbit
the
because
rings back. Yeah,
EP. Yeah, interesting. Very interesting.
because I'm
I mean,
just I'm not sure like how
we've
you
got quarter.
like if even if you get this like the Starship working, like it just feels like the wear at those temperatures, it's just going to be so hard to get into that rapid reusability cycle.
I agree. It does seem like an incredibly difficult problem to solve, and I do wonder if they can make it affordable and rapidly reusable.
Yeah, and then
Yeah,
that same technology could be used to, fling them at Mars and catch them in Mars and like have that trip become much shorter.
mm.
Like the best railgun on Earth can do like it if you put it in space, it would take 2 months to get to the sun. But like which is like way better than the timelines that we're talking about for some of these shorter distances. And if we even
How big
took,
is this ring? Like,
so
yeah, just get into it a little bit. How big is this? Like, so this ring is like, so Starship is a 9 meter diameter. So the
yeah.
ring is like a say 15 meter diameter.
Yeah, or maybe a bit bigger in case your aim's a little off. You don't really want to be shooting quickly through these things and hitting them.
Yeah.
But yeah,
And then how deep is it? Like, how long does it run?
so you just need a few of them in series because I mean,
So
if you're taking,
each one could be like a meter deep.
yeah, yeah. I mean, I haven't done that sort of specifics on. I was more concerned with how much they needed to be spaced out because
Yeah.
otherwise, the G-force, like if you want to be able to use this for anything with a human in it or that's got a G-force sensitive payload, you're going to need to space them out a little bit so that you're not sort of putting all that, deceleration in like at once. Um,
Mm. Mm. Very interesting. It's a very interesting concept. There's nothing springs to mind for why that wouldn't work immediately, but so your spacecraft. Let's say you want it to go from 27,000 kilometers an hour down to um,
about 13 would do it because then you probably wouldn't need any form
13.
of shielding at all.
And let's say you're going to have five in a row. So let's say you want to reduce its delta V by or its velocity by 2,000 kilometers an hour. Does that mean it's going through the relative velocity is going through at is 2,000 kilometers an hour,
Yeah, yeah.
or maybe faster? and it comes out. So yeah, so and then the ring presumably is then going 2,000 kilometers an hour faster, so it's in a elliptical orbit with a higher apogee at that point, and then it maybe probably then takes like a few weeks to use EP to get it back to where it was.
Correct. Yeah, yeah. So you'd sort of, for every Starship you wanted to bring down, you'd need a month between, your series of rings in terms of the station keeping kind of ion thrusters. So, it just
Hmm.
depends how often you want to bring one down as to how many of these series of rings that you need.
Yeah, I mean it'd be bloody hard to hit a 15-meter diameter ring at 2,000 kilometers an hour in space, but maybe I mean it's definitely not against the laws of physics.
Well,
It's
if you
definitely.
had, 10 times as many rings, maybe the problem gets a little easier. Or maybe they kind of like synchronize with each other and then it exits at
Oh,
2000 rather than having to enter it at that speed.
I see. Yeah, the ring like pushes it back and thrusts itself off in the other direction.
Yeah.
Hmm, interesting. So, I mean, is anybody looking at this? Is it like, is there a company?
Um,
So,
I haven't the closest I could find when I was looking at this were these ideas of these sort of like these lines that would kind of swing down and create this kind of um you'd basically have these sort of spinning, I don't know, ultra long carbon fiber sort of fishing lines that would sort of, the speed they're traveling, they'd kind of have this sort of moment of like kind of, moving at the same speed as the Earth's surface. So you get this kind of like pick up and drop off effect. Um, but that all seemed like, I don't know, sort of space elevatory, like to, futuristic materials needing for
yeah.
to be practical. So
Have you
uh,
spent time looking at space elevators? Any thoughts there?
um, it just seemed like the degree to which we'd need to develop the carbon fiber or whatever you're going to use for uh
Yeah.
it just seems like so far away, and also just sort of so like so many unnecessary complexities. There's such a target for any kind of like geopolitical threat, and
Yeah.
they'd just be so
And
finicky.
also they would just get continuously peppered in Leo by anything, any fleck of
Yeah.
paint is going to hit this thing at 27,000 kilometers an hour.
Yeah, and then I was looking at like just even easier versions of that. I think it was Everyday Astronaut did a good one on like, wouldn't it be better to launch rockets off the tallest mountain because then you'd need less fuel and all
Yeah, I
that.
saw that. I
And he's
saw
like,
that.
yeah, it would be like 10% better, but that 10% doesn't make up the logistical cost of getting the stuff to the top of the mountain. And I'm like, well, if you can't even be bothered just like going up a mountain that's already here, like why would building space like, you know,
Yeah, yeah, makes sense.
and then
Yeah,
we've got those kind of the carrier launches where you go and take the vessel up as high as you can with a plane or a balloon or something, and even it's just too fiddly. So, and that
yeah,
all seems like many orders of magnitude easier than a space elevator, and even that it's just like look, just keep it simple. Like, all right, you got to put some more fuel in. Okay, put more fuel in. Right, a bit less
yeah.
payload. Keep it all simple. There's enough going on already. So yeah, it
Yeah, he
seems
did a
like.
good one recently on cannons and shooting stuff, and
Oh
basically
yeah, the
same
space
conclusion.
guns. Oh, I'll have to see that. I
Yeah.
got so obsessed with space guns. I really went down that rabbit hole.
Nice.
Did you hear about the space gun guy? Like what happened to him? So he
Were
was he was
called
working for
what's
some
it
guy.
called?
So
What?
ah,
Not spin launch, but the other one.
no, this was like decades ago.
Oh, okay,
Um,
okay.
and so it almost got the space guns figured out, and then it didn't go ahead, and he ended up joining up with some sort of foreign state actor that wasn't amenable to a bunch of other parties, and because he just had to see this space gun thing through, but ultimately, like some security forces decided that wasn't how he was going to spend the last of his days and things. So.
Took him out.
Uh, yeah, they're like, we might not want a space gun, but we certainly don't want anyone else having a space gun. So,
Yeah. Tough life. Yeah.
yeah, yeah. No, I think I'll stick with the rings, and for the great, the Western countries that we're all in, I think it'll be great. And yeah, I'm gonna try developing that. Cool. Okay.
Yeah.
So maybe just sort of lastly, you could comment like this is heating up now, right? Like it seems like there's a lot of folks who are really interested on this. Like what what do you think's the most interesting with other folks working in the space that you're in right now?
I mean, it's certainly very interesting that Eric Schmidt said that he bought relativity space in order to build data centers in space.
Seems like
But
he's just missing the data center piece.
yeah, exactly. Because I mean, I think I'm going to meet him in August. Actually, there's a conference I'm going to in London where he's going to be at, and I'm certainly going to try and track him down. Um, he keeps getting asked about it as well. Like he got asked about it recently, and he was on stage somewhere, and he just said yes, and then he stopped talking, and he said, "That's all I'm going to say." So definitely, that's interesting. I think Sam Altman is like keeps hinting that he's heading in this direction. And I'm still shocked that Elon hasn't started picking this up yet. I guess he's so busy building these colossus data centers on Earth, and rightly so, because we're not going to be, it's decades away before you can build a colossus in space. Um, but I'm surprised he hasn't, I have not heard anything from him about it yet. So, except that
The
he thinks
silence is deafening.
the science is deafening, like the silence of the cosmos.
Philip, great to speak with you, man.
Great to speak with you too.